I will be solving problem 5.41 from Griffith's Introduction to Electrodynamics. So a current I flows to the right through a rectangular bar of conducting material in the presence of a uniform magnetic field B pointing out of the page. So we can start with A. If the moving charges are positive, in which direction are they deflected by the magnetic field? So let's write down the equation of the force due to the magnetic field. Force due to the magnetic field is QV cross B. And the question specifies that the moving charges are positive. And conventionally, the direction of the current is the direction that positive charges move. And we have current going to the right, which means we have these positive charges moving to the right. In this case, the charge Q equals positive Q because the charges are positive, where Q represents the magnitude of the charge, and we are given that these charges are positive. So we can substitute this into our equation. Equals positive QV cross B. Then going to write here the magnetic field is out of the page. And using the right-hand rule, you get B in this direction, B out of the page, and get a force due to the magnetic field downward. So we'd have the slab with these positive charges accumulating at the bottom. And because of this, we would have an electric field pointing upward. So now we move on to part B. Find the resulting potential difference, the Hall voltage, between the top and bottom of the bar in terms of the magnetic field B, V, the speed of the charge, and the relevant dimensions of the bar. So to find this potential difference, we can use this equation. VB minus VA equals negative the integral of E dot dl. And this goes from A to B. So we can take our coordinate system to be y in this direction and x in this direction, and we can set the bottom of the slab here equal to 0. Then we would get that delta V would be equal to negative the integral y equals 0 to t, which is the thickness of the slab that you see there. And E dot dl. So because the positive charges accumulate at the bottom, as shown in the previous question, we would have an electric field pointing in this direction. And this direction is the positive y-hat direction. So from this, we would get that E equals E in the y-hat direction. So I will write that here. So V dot dy in the y-hat direction. Now we know that y-hat dot y-hat is equal to 1. So we get negative E y equals 0 to t dy. would end up with potential difference is equal to E times T. Now they want it in terms of magnetic field, velocity, and dimensions of the bar. So what we can use here, so because we're looking for the potential difference from when the system is in equilibrium, and the system is in equilibrium when the force due to the magnetic field in one direction is equal to the force due to the electric field in the opposite direction, we can use that to solve for the electric field in terms of the magnetic field and velocity. So I will erase this really quick to make space. So we can write that the force due to the electric field is equal to negative the force due to the magnetic field. And we know that this is equal to QE. This is equal to QB cross B. So we already established that the direction of the E field and the B field are both in the y-hat direction. So we can do this. QE in the y-hat direction is equal to negative QBB in the y-hat direction. And we can cross out this, get E in the y-hat direction equals BB in the y-hat direction. We then take the magnitude of this to get E equals BB. Next, we can plug this into our equation for potential difference. So we had delta V equals negative ET. And when substituting this in, we get delta V equals negative VBT. So this tells us that as we're moving from 0 to T, which is the top of 0, which is the bottom of the slab, to T, which is the top of the slab, our potential is decreasing. So now we move on to part C. How would your analysis change if the moving charges were negative? Again, we follow the convention that the direction of the current is the direction that positive charges move, and we have current going to the right. So the direction of our negative charge carriers is going to the left, is moving to the left, with some velocity v. And we still have the magnetic field pointing out of the page. So again, we want to look at the equation for force due to the magnetic field equals QB cross B. But in this case, the moving charges are negative. So this Q is actually equal to some charge negative Q, where Q is the magnitude of the moving charges, and negative just indicates that they are negative moving charges. So we get that the force due to the magnetic field is F of B equals negative Q V cross B. So again, we use the right-hand rule. We have V going in this direction, B going under the page, and our charges are negative, so it's actually flipped. And the force due to the magnetic field are actually going down. Force due to the magnetic field is going down. So what we get in this case is that the bottom of the slab, we have these negative charges accumulating, and the electric field we get is in this direction, which is the opposite direction of what we had before. And because the direction of the E field is now in the opposite direction, we get an opposite value for potential difference. So previously it was delta V equals negative VT, but now
we have delta V equals positive VVT.
So this is saying that as we go from the bottom of the slab to the top of the slab, the potential increases.